Swayam Prabha. Digital India. Educated India.
Okay, today we will be looking at transformations, that is rotation transformations and translation transformations. So just quickly revising about rotations and transformations. So we have a two link manipulator system here. So this has two revolute joints, one revolute joint here, one revolute joint here, and there is an end effector there. So as explained in the last class, how do we proceed is essentially we fix an axis here. Say I call my one axis here and another axis there. I call this my x axis, my z axis is perpendicular, and this is my y axis. Similarly, I put one axis on this joint and one axis on that joint. Now if I want to move the robotic link, so I need to change the link variables. So we have one link variable here which is theta1, and there is another one there which is theta2. So if I change one of the link variables, you can see that let me put the first link variable to be 30 degrees and the second link variable to be also 30 degrees. And what we see here is that if I do that, then the link moves to the position where this angle is 30 and this is 30. So what this means is that basically I need to know, if I want to position this end effector at some point in space, then I need to know what is the corresponding angle. Now how do I know that is essentially we need to assign axis at each of the frames and then find the relationship between this frame and then this frame and this frame with respect to the base frame. So what this basically boils down to is that we need to know the frame to frame rotations. Now if you look at the frame to frame rotations and translations, there are two operations that go on. One is a rotation, the other is a translation. So if you look at the frames, let us go back to this again, that we have two frames here. One frame is my 0 axis which is assigned to the base frame. So this is my 0 which does not move. Now I assign the first frame to the first link. So this is my first link, and if you can see through here, that is my first axis, my x1 here, right, and the z1 is also aligned with the x0 and it is the same axis. Now when the link moves, what will happen, this x0 and this x1, the angle between them will change, and that is what I call my theta1. Now if I assign another axis here, the z is coming outward, and I assign an x2 here, then I say this is my x2 axis on the link and this is my x2 axis. Then there is an angle between the x1 axis which is like this and the x2 axis which is there, that is my link variable theta2. And I can assign a third axis here and call it the x3 axis, and the z3 axis is like this. So essentially this means that if I want to go to some point in space, essentially I will need to know the relationship between this frame and this frame, and then this frame and this frame, and then the frame 1 with respect to the frame 0. Now if you see what is the difference between the frame 0 and the third frame, this third frame here or the second frame here essentially has translated. It has, so the origin of this frame has moved from here to here. It is in this distance now, so it has translated from here to here. And the second is there is an angle between this x2 and this x0. So this frame has an angle and a translation distance with respect to this frame. This frame has only an angle with respect to the frame 0. So essentially this shows that we need to know two transformations. One is the rotation transformation and the other is the translation and rotation transformation. Now in the last lecture we had looked at the rotation transformation, and we found that if there are two axes, I have an axis which is the reference frame which is not moving. Let me call this x, y and z axis. So the x, y and z axis is not moving, we say is the fixed frame or the 0 frame. So this is not moving. Now if there is another frame which is rotating on that, so I have another frame which is rotating. Let me call this my x1 as I have drawn in the two link manipulator system there, and this is my y1. Then if I have a point which is here, let me call that point BP, and BP basically means the point is P and with reference to frame B. So this is my frame B, this is my frame A, right. So when we say coordinate of this is UVW, it is basically means this is the distance of this point projected on the x-axis and the y-axis, so that's my u, v and w. And when we say the corresponding point AP has coordinates x, y, z, then essentially what we mean is the projection of this this point on the x axis. So, this is my x, that is my y, and there is no, and the projection on z is not there because both of the axes are the same. So, what have we done here? Essentially we are saying that the axis B has rotated by an angle theta about the z axis. Okay. And in the last class we did find that if I want to find the relationship between A and the relationship between x, y, z and u, v, w, how do we do that? We can very easily find from geometry. So, we make this geometrical construction, and from here we can derive that x, y, z in matrix form, if I write, is equal to cos theta minus sin theta 0, then it's sin theta cos theta 0 0 1, and here is my u, v, w. So, in the last class we had seen that this matrix is called the rotation matrix, and it is expressed as rotation about z by an angle theta. It has important properties. It is a proper orthonormal matrix. So, R inverse is equal to R transpose, and the determinant of R is equal to 1, and each of the columns, that means the mod of x, the mod of y and mod of z are equal to, is also equal to 1. Now, this is what I mean by the columns x, that is the column y, and this is the column z. Now, this rotation matrix gives us the relationship between the coordinates of a frame which is expressed in a rotated system to that of the reference system. So, essentially it gives us the relationship between a frame A, frame B and frame A. Now, as we have seen there, as we have seen in the two link manipulator system there, now we can have a rotation and we can also have a translation. Now, let us see if the frame rotates and also translates, then what does it look like. So, again we start off with the assumption that this is my base frame, and this is the x, y, z of the base frame which is not moving. So, this is not moving, let us call it the frame A or the frame 0, and we have another frame which is initially the same. Let us say initially my B frame is the same as frame A, but then it rotates and then it translates. So, it rotates like this. So, this is my frame B, it has rotated by an angle theta, and then what happens is this frame has moved from here to here. So, if you can imagine, this frame has moved here now. So, it is rotating and also translating. So, my frame B is no longer here, it has rotated and it has translated. So, first it rotated by an angle and then it translated. So, this takes care of the rotation and the translation at the same time. Okay. Now, I want to find the relationship between the two frame, between the coordinates of a point expressed in frame B. So, I have BP here now, which means the point is P and the frame is B. Now, if this has coordinates u, v, w, if this has coordinates u, v, w, okay, what does u, v, w means? It is expressed in frame B. So, the projection on this is u, that is v, and w is on the x axis, on the z axis. So, this is my x, y and z of frame B, which is u, v, w. Now, if I want its coordinates in frame A, then AP is equal to x, y, z, right. Now, we find that unlike the previous case, if you just see here, the origins were the same, there was only an angle between them. But now, if you look at the two frames, this frame has an angle plus it has moved. So, the origins are no longer the same. So, the origin has moved till there. Okay. So, from here the origin has moved. So, from the origin of this, the origin of the frame B has moved there. So, this is my frame B, right. Now, this is my BP which is expressed here. Now, I want to know what is the relationship between this x, y, z and u, v, w. How do I get that? Is essentially we close this vector loop diagram, and we see that the distance from here to here is given by AP B org. This is the standard way of writing. It basically means this is the distance between the origins of two frames A and B. This is my AP, which means the coordinate of the point P expressed in A. So, this is my AP, this is my PB org. Now, this is my BP, right, which is a coordinate of point P in frame B. Now, if you look at this, we basically see that we can express this vector closed loop as ABP org plus BP is equal to AP, right. So, if I write it here, it becomes AP is equal to APB org plus BP. Okay. In terms of vector closed loop. Now, we need to note something here is that this vector BP is expressed in frame B. Okay. So, we can't add it like this because this is expressed in frame A, whereas this is expressed in frame B. So, we cannot add two vectors which are expressed in different frames. So, what do we do? Essentially, we convert the coordinates of the point B in frame A by putting a rotation matrix. So, I put a rotation matrix here and convert this this point P, which was expressed in B, to that of A. How do I do that? I simply add a rotation matrix there. Now, I can add it. Now, once we have added it, what we do see is that if I write it in a 4 by 4 matrix now in matrix form, then AP, the coordinate of AP is x, y and z and 1, and this one is a 4 by 4 matrix which is written this way. So, this part is my rotation matrix which is here. So, this part comes here. So, this is cos theta minus sin theta, this is 0 0 1, and this is sin theta, and this is cos theta, this is 0 0 1. So, my rotation matrix part has come here. This is also 3 by 3 matrix which is a rotation matrix. This APBORG, which is the distance between the origins, comes here as, let us call it x dashed, y dashed and z dashed. What is x dash, y dash, z dash? It is the distance between the origins. So, this is my x dashed, that is my y dashed, and z dashed is in the z direction. So, the distance between the origins are coming here. The rotation matrix is a 3 by 3 matrix which is shown here. Now, here we have 0 0 0 and here we have 1, and on the other side we have u v w and 1. Now, essentially what this means is that this is a transformation matrix which is converting the coordinates of a point expressed in a rotated system and translated system to that of the reference system. So, if you have two axis systems, one of which is rotated and translated with reference to the base, then essentially this homogeneous transformation matrix is the one that relates the rotated system to that of the reference system. Now, in case you are wondering how is this 4 by 4, then essentially we know that in 3D Euclidean space, we have 3 parameters, right. That is why it is called 3D. Now, in this Euclidean space, the rotation matrix takes away the 3 parameters, because this we have seen in the last class that this also requires 3 parameters, which means that in order to express the rotation of an object in this frame, we need 3 parameters, that is the angles it makes with the x, y and z axis. Now, in Euclidean space we have 3 parameters. These 3 parameters are taken off here. So, we cannot express rotation in translations also in Euclidean space, because of which we have to move from 3D Euclidean space to that of 4D homogeneous space, and this is called a homogeneous transformation matrix. So, this is a 4 by 4, it is called the 4 by 4 homogeneous transformation matrix. So, this transformation matrix essentially relates between two frames which are rotated and translated. Now, this has names. This part, let us look at the next. So, let us look at this in a little bit more detail. What does this part mean? This part essentially, so if you look at this part, this is the rotation part, which is essentially the rotation between this frame and this frame. In this case, it is a rotation about z, so it is having the structure of cos minus sin, sin cos. This is the distance between the origins. So, the distance between the origins is from here to here. So, this is in the x direction, it is x dash, in the y direction it is y dashed, and z direction it is z dashed. This is always 0 0 0 and this is always 1. So, this is the coordinates expressed in frame A, this is the coordinates expressed in frame B. So, if I give you u v w, we can just multiply with this and get that. Now, this has names. So, the names of this matrix, 4 by 4 matrix, let us look at it. So, the 4 by 4 matrix essentially is of this structure. So, this part is called the rotation part, which is 3 by 3. The rotation matrix, in most cases it is rotation about z axis. This is my translation part, let us call the translation part, which basically is the distance between the origins. Distance between origins of the two frames, the reference frame and the rotated translated frame. This is called perspective. and this is called scale. Okay. So, in robotics the perspective here is always 0 0 0 and the scale is always 1. So, this matrix is 3 by 3, this is 4 by 1, sorry, it is 3 by 1 here, this is 1 by 3, 1 cross 3, and this is 1 cross 1. So, these are 4 matrices and they have names: rotation, translation, perspective and scale. And we should be very we should understand this very clearly, that what does it essentially mean, that it basically means the angle between the 2 frames, this is the distance between the origins, perspective is always 0 0 0 and scale is always 1. So, if you do a very small example, that if we have a frame A, we have a frame B, okay, B is rotated and translated. So, let us say it is rotated by 60 degrees about z axis of A, where A is the reference frame which is not moving, and translated by say 2 to 2 units in x, y and z directions of A. Okay. So, what does this mean? If you come back here, we have 2 frames A and B. This frame B has been rotated by 60 degrees about the z axis, and then it has been translated from here to here, and the distance is 2 units here, 2 units on the y axis and 2 units on the z axis. So, that is what the question says. Now, if you are given the coordinates of a point, if you are given BP, for example, the coordinate BP is 1 1 and 1, we are asked to find what is AP. Okay. So, the question says there are 2 frames, one has been rotated by 60 about z axis of A and translated by 2 to 2 units in the x, y, z directions of A. Now, if the coordinate of point B is given, then what is the coordinate of point A? How do we find that? It is very simple, we simply use this matrix. So, the coordinate of the point P in frame A is given like this, multiplied by the homogeneous matrix which is given on top. So, first we write it has 4 parts, this is always 0 0 0, this is 1. Now, the rotation matrix is a rotation by above the axis have rotated by 60 degrees about z axis. So, this is cos 60 minus sin 60, 0 0 1, this is sin 60 and this is cos 60. This is 0 0 1. Now, the distance between the origins is given by 2 to 2 units. So, it is the origin distance is 2 to 2 units in the x, y and z directions. And what is the coordinates of the point P? It is given by 1 1 1 and 1. So, all I need to do is simply multiply this out, find the values of cos and sin theta, sin 60 in this case, multiply it out and I get the answer. Okay. That is very simple to do. But what is more important is to understand in the 4 by 4 homogeneous matrix what each of the parts of the matrix mean. Now, what is the inverse of the homogeneous matrix? So, we have seen that the inverse of the rotation matrix is equal to its transpose, because it is a proper orthonormal matrix. Now, what is the inverse of the homogeneous transformation matrix? If you can imagine a little bit here, okay, it is a little bit of imagination here. Now, if we say how did this frame go here? This frame rotated and then it translated, right, that is how it went there. Now, if I say if I want to bring it back and align it, which is like what is like saying what is the inverse of that, then essentially I need to rotate it, which is inverse of the rotation matrix, and I need to move it in the negative direction like this from here to here, right. So, I have to move this origin from here to here in the negative direction, plus I have to rotate it and align it with this, which is the rotation matrix. So, the inverse of the transformation matrix, the homogeneous transformation matrix, so we can call it T inverse, looks like, so the inverse of the rotation matrix is the inverse of the rotation matrix, which is inverse, or I can write this as transpose, which is the inverse. Okay. Next, we have seen that we need to take the negative of the distance between the origins. So, I do a minus of x dashed, y dashed, z dashed, okay, that is a minus of that, because it has to move backwards, and then it is multiplied by R transpose again. okay, and this remains as 0 0 0 and this remains as 1. Okay. So, the inverse of the homogeneous transformation matrix is given by this matrix, and we are able to understand. We can understand, or we can very easily visualize why it is like that. Now, if we are having compound rotations, suppose we have compound rotations, so first I rotate about an axis A. So, first I am going to rotate about the z axis by an angle alpha, then I am going to rotate about axis x of fixed system, fixed x, by an angle let us say beta. Okay. So, first is my rotation about the z axis by alpha, then is the rotation about x axis by an angle beta. So, we know the rotation matrix for this, and we also know the rotation matrix for that. So, now if you want to find the combined rotation matrix, then what we need to do is we need to multiply rotation of beta versus rotation of alpha. Okay. So, this basically means that the rotations have reversed. So, this was 1 and this was 2, but when we are writing, we are pre-multiplying the rotations. So, we are pre-multiplying the rotation matrices. Now, again we need to understand this a little bit. Why is the order reversed? So, why is the order reversed? Okay, so, this is a question that might come to your mind. So, we can very quickly look at this, that in this example, that if I do have x, y and z axis. So, I have an x, y and z axis here. For example, I have an x axis here, y axis here, and a z axis is here. Okay, so, this is my z axis. So, let us I hope you can visualize this. So, this is my x, y, and this is my z, and as per right hand rule it is x, y and z. Now, suppose I have a point here in space which is given by a point P. Now, this point P, this is a vector which is connecting to the origin. So, this is my point P. Now, suppose I rotate it about the z axis. What does it mean? I am going to rotate this point which is here, let us say it is here. I am going to rotate it about the z axis. So, if I rotate about the z axis anti-clockwise, okay, so let us try to understand why we need to pre-multiply. So, this very simple example will explain why we need to pre-multiply. So, let us look at this table. You can imagine that this is an x axis, this is my y axis, and this is my z axis. So, let us look at this table here. So, there is x axis, y axis, and the z axis. Now, if we have a vector here in space, say let me say this is a vector, and this is a point P which is expressed here. Now, I rotate it about the z axis. So, I am going to rotate anti-clockwise. So, it comes here, okay, after some rotation by theta, right. So, that is my first rotation. Now, I am going to rotate it about the x axis. Where is the x axis? It is here. So, if I rotate it like this, then what will happen? This will come down, right. So, first rotation, I will repeat, is about the z axis, then the rotation is about the x axis. Okay. So, where did the vector come? It has come here now. Now, suppose I want to bring it back. How do you bring it back? So, first what we will need to do is rotate it about the x axis and then rotate about the z axis. So, this shows that what we did is we were here, we rotated about z, then about x, but then when we are multiplying, finding the combined matrix, then what we are doing, we are first reversing the second one, that is we are rotating about x, then rotating about z. Now, this essentially explains why you need to pre-multiply this order of pre-multiplying the rotation matrix if you want to get the combined matrix. Now, in case of the homogeneous transformation matrix, next what we will need to see is what we call the DH parameters. Okay. So, the Hartenberg parameters. Okay. Now, what the Hartenberg parameters tells us, it basically tells us how to assign the axis in space. Assign the axis. Now, what do we mean by assigning the axis? It essentially means that the x, y, z can be taken in any direction, because they are just directions in space. So, you can take the x direction like this, or you can take it like this, or you can take it like that. Okay. So, it does not matter. So, there should be some uniform way, or a uniform way of assigning axis, which makes it simple. So, Denavit and Hartenberg in 1960s, about 1960s, 1968 I think, they developed a system by which you can start assigning the axis, which makes it very, very simple to perform your homogeneous transformation matrices, and this in short is called the DH convention, DH matrix convention, and in short called DH. Now, one point before we proceed is that when we are multiplying rotation matrices in 3-dimensional Euclidean space, so this is 3-dimensional Euclidean space, we pre-multiply. But when you are multiplying the homogeneous transformation matrix, for example, my matrix T, I am going to multiply the matrices T, then in that case we do not change the order. So, please do remember this. Okay. So, this is T into n minus 1 into n. Okay. So, here you see the order is not reversed. And essentially because why? Because first of all the origins are different in the frames here now, and this is in homogeneous space. So, this is 4D homogeneous space. So, please note this, that when you are multiplying matrices, only matrices, then you reverse the order, but when you are multiplying the homogeneous transformation matrix, that means when you are finding the matrix, each matrix for each joint and then multiplying them out to get the final 0 to n matrix, then you do not change the order. So, note that order is not changed, okay, essentially because the origins are different here in the two frames and we are in homogeneous space. Now, so how do we assign frames? Now, let us look at this again. Okay. So, this we come back to our 2-axis link here. So, this has 2 degrees of freedom. What are the 2 degrees of freedom? The first degree of freedom is so let us reset it to 0 0 again to better understand what are the degrees of freedom. So, now we are resetting it to 0 0. So, let us assume that this is my x 0, the first frame is going to be here. So, it is rotating about this axis. So, this is the axis of rotation of the first joint. So, if you look at the axis of rotation of the first joint, let us move the first axis by 30 degrees. So, I am moving my first axis by 30 degrees. You can see that it has moved by 30 degrees and it has come here, right. That is the motion of the first axis by 30 degrees. So, what is that 30 degree? If this is my x 0, that is my x 1, then this angle is 30 degrees. Next, I move the second axis also by 30 degrees, and we can see the second axis moving now to 30 degrees. So, what changed? If you see, if this is my x 1, this is my x 2, then this angle changed. So, the reference angle between this and this changed. Now, DH parameters essentially tells us that how do we assign our axis such that it becomes very, very simple and you need to do the least number of computations. Now, so what DH parameter says is the axis of rotation, in this case it is an axis of rotation, or the axis of translation is the z axis. So, in this case z0 is here, the reference which does not move, z1 is fixed onto the first axis or the first link, which is this one. So, both of them z0 and z1 is the same axis. Next, z2 is here. So, this is my z2 axis, this is also a revolute joint. So, my z2 axis is here, and there is a small link there which can rotate about that, if you can see. So, this one is my z3 axis now. Okay. So, DH tells us that we assign the z axis first about the axis of rotations or translations. So, z0, z1 are here, z2 is here and z3 is there. Next, it says the x axis is to be assigned. The first one x 0 can be assigned like this, which is the reference frame, it does not move. Then the next x is assigned along the link. So, my x1 is assigned here along the link, x2 is here assigned along this link, and x3 is there assigned along that link. Okay. So, we have 3 origins, z0, z1 here, z2 the second origin is there and the third origin is there. Z axis are pointing outward like this, and the x axis, in the first case the x axis is like this, the second one it is along this link, third one is along this link, this is the first one, second one, and the third one is there also, it is along that link. Okay. So, the DH parameters convention is quite simple to follow. It says that the first axis is your axis of rotation or translation. So, z axis along axis of rotation or translation. Okay. So, we have fixed our z axis. Next, x axis is along the link, which also I explained here what is along the link, and x axis is the shortest distance between the z's. So, which is also the shortest distance between the z axis. Okay. So, we fix our z axis, then we fix our x axis. Now, there is a possibility that if the z's are intersecting, then there is no shortest distance between them. In that case, if z's, so this is a sub clause here, if z's are intersecting, then x is perpendicular to plane containing z's. Okay. So, this is the first one, how to put your z axis. Number 2 is how to put your x axis. Okay. So, let us look at the same example that I showed here, that is shown just a few moments back about the 2 link arm. If I were to draw it here, so I am going to draw it like this. The first link is like this. In this configuration, if you see, the second link is like that, and the third one is like that. Okay. So, this is exactly the one that is shown here. Now, how do I put my z axis? Z axis is axis of rotation or translation. In this case, it is rotation, so it is rotating on this plane. Okay. So, the z axis is outward. So, I put first fellow which does not move, z0, and the first one is z1. The second one is here, which is z2. The third is here, which is z3. Right. So, that takes care of all the z axis. Next, I have to fix my x axis. Now, the x axis, the first x axis is taken like this as a reference, again convention, okay, which does not move. So, z0 and x0 do not move, they are fixed frames. The next is, it is the shortest distance between the z axis. So, it is along the frame. So, this is along the frame, this is my x1. This is the shortest distance again between this z and this z, they are parallel. So, this is my x2 and my x3 is here. Okay. So, we have fixed my x, y and z. Now, we know that x, y, and z, the moment you fix x and z, the y gets automatically fixed. So, if x is here, then as per right hand rule, y has to be there, okay, as per right hand rule. So, it is x, y and z. So, y gets automatically fixed, and because of which we do not normally indicate y. So, y is normally not indicated, okay, in robotics, because the moment you have fixed x and you have fixed z, then automatically y gets fixed, and there is no need to draw it and show it. A few other parameters let us draw. So, let us call this L1 and let us call this L2. Okay. So, we have now assigned our frames as per DH notation. So, this is what we call by DH notations, the Denavit-Hartenberg parameters. Now, let us look at the second case where if the z's are intersecting, here the z's are parallel. So, we were lucky that then this x is defined as the shortest distance between them. Now, in case the z's are intersecting, if you can imagine this case where we have another manipulator like this. So, we have a manipulator which is like this. So, if you can imagine this, now if you can imagine this manipulator, how it moves. This is one manipulator, this is a robot arm in which we have one axis, the first axis, which is rotating about this, you can imagine this. So, this is rotating by angle theta, either that side or this side. So, the vertical axis is this axis, the vertical axis, and it is rotating about this. Now, the second axis, so this is my z0 and z1, the first axis is 0 and 1 are the same axis about which it is rotating. The second axis is the one that is translating. So, there is a translating axis here. This part can move in and out of this part 2. So, if I call it part number 1, part number 2 and part number 3, then part 1 can rotate, part number 2 is sliding in part number 1. So, it is sliding means this is a translating motion. So, the z axis z2 is like this. Okay. So, this is my z0 z1, let me draw it, and this is my z2 here. Okay. And the part number 3 is here. Now, part number 3 can also rotate. So, it is a rotating joint. Now, if it rotates, then this is my z3 here. Okay. Where are the origins? Let us assume the origin of 0, 1 and 2 are here, origin of 3 is here. Now, please note that the origin of frame 2 is on link 2, which is inside. Okay. So, when it moves, the origin will actually move. So, in this case, basically what we are seeing is that we have the z axis z1 and z2 which are intersecting here. So which means that if you try and look at how to assign the x axis, we have to use this clause here, that if the z's are intersecting, then x is perpendicular to the plane containing the z's, and in this case z0 z1 there is no problem, they are the same axis, but z1 and z2 they are intersecting. So basically x has to be perpendicular to the plane which is containing the z's. So which is the plane containing the z's? This plane is the one containing z's, so x has to be perpendicular to that. So we put all our z0 x0 x1 and x2 on the same axis, and they are perpendicular to the plane containing the z's. The x3 we can put it here, which is along with this, right. So this is an example to show where the z's are intersecting. Then what do we do? Now the more important part of DH parameters is if we are moving from one frame to another frame in a space. Okay, so let us have a look at, this is a very simple case that is shown, two links or a 3 degree of freedom planar robot. But if you look at more complicated design, this is also pretty simple. But if you look at a more complicated structure, which is very generalized structure, let's look at this. So this is a generalized structure. Okay. So the shape of the link can be any shape. So let's say that the shape is in 3-dimensional space, it has a funny kind of a shape, and it can be anywhere. So the shape actually can be anywhere, right. Now this is a revolute joint. So this is a revolute joint. Now I am going to assign the axis as per DH notation. So the first axis is a revolute axis, so there is one more here which is on this side, right. So it's like a tree branch which is going from one link to the other link, but they have all funny shapes. So this is my z axis, which I first put as z. So let me call this zi minus 1, which means this is the z axis. Now an axis can move in, can point upward or it can point downward towards infinity, because an axis is a line, right, and it goes from infinity on one side, from plus infinity to minus infinity. So just for convenience, or we say that this is my positive z, okay, and mark it that way and say this is my z axis. So this is the first one. The second one is here. So this is my z, zi. Okay. Now I mark my origins and say this is my origin of I minus 1 frame, and this is the origin of my I frame. Okay. Now I mark my x axis. So x axis I am going to mark like this. Let's say this is my xi minus 1. Okay, shortest distance between the z's, and on this side it is here, so it is xi. Okay. Now the question is, I want to find the relation between the frame I minus for the frame I to the frame I minus 1. That means what is the relation of a point expressed in frame I to the frame I minus 1. Okay, how do I find that? We have assigned our frames as per DH parameters. Now we need to see if I want to take this frame from here to there, from this point to this point, then how many transformations are required. We have seen that essentially you have two kinds of transformations, rotations and translations in space. But if you are going from one frame to another frame in space, then what is the minimum number of transformations, rotations and translations that you require to go from one frame to another frame. So that is what DH parameters is useful for, because it gives us the minimum number of transformations required. Now if you have more number of transformations, you will have more multiplications. So the minimum number is the best, because there is no point in having more transformation matrices, your complexity increases. So how is this done? So essentially what we are saying here is this, I want to take frame. So let's look at this frame here. I want to align this frame, the I minus 1 frame, to the ith frame. How can I do that? Now let's look at, let's have a look at how can I do that. So first of all, I see that the angle that the xi minus 1 axis makes with the xi axis is different. So what I do is I shift this axis like this. Okay. So this is my xi axis, and make it parallel. So now this and that are parallel axis, right. So what I have done first is I have taken the zi axis and made it parallel and moved it such that it is parallel, these two axes are parallel now, or in other words I have taken the xi axis and moved it here by an angle alpha, right. So now xi and these two are parallel, so these two are parallel lines, and I have rotated my xi minus 1 axis by an angle alpha and made it parallel to the zi axis. So, what we mean here is that the first operation is take this axis, rotate by an angle alpha and make it parallel to the z I axis, right. Next, what we do is we move the origin from here to there. Okay. So, now if I move the origins from here to here by a distance a, let us call this distance a I, this is my angle alpha I. Okay. So, now what would happen is your z axis is already aligned. So, my new z I minus 1 is here because it is aligned with x I with z I, and the origin has moved from here to here. So, the origin is also here, but my x axis is in some other direction. So, the x I minus 1 is here. So, x I minus 1 is here. So, this involves two operations. One is moving the rotating angle z I minus 1 by an angle alpha, and then moving the origin by a distance a I from here to here. Now, we can see that the origin is on this axis and but the x's are not aligned. So, what I do next is I rotate this x axis x I minus 1 by an angle theta and make this parallel to that. Okay. So, this is my new x I minus 1. Okay. I have rotated the old x I minus 1 by an angle theta and made it parallel to the x I. Now, the z's are aligned, the x's are also parallel to each other, but the origins are still not the same. So, I move the origin up by a distance d I. Okay. And this now after that what would happen is essentially what we will get is now the origins are the same and the axis of the z axis and the x axis of both the frames x I and x I minus 1 are the same. Okay. Now, how many transformations were involved, how many rotations and how many transformations. So, first what did we do? First we moved by alpha, which is I moved the z I minus 1 by an angle alpha and made it parallel to the z I. Then what did I do is I moved the origin by a distance a I from here to here. Okay. So, next was a I, and then what did we do is we rotated by an angle theta. So, the third transformation is theta I. We rotated the x axis by an angle theta and made it parallel to the x I, and then the fourth one is we moved the origin by a distance d I and brought it here. Okay. So, these are the four parameters, this is the four transformations that we carried out. So, this is a rotation, this is a translation, this is a rotation, and this is also a translation. Okay. So, each of this would be a 4 by 4 matrix. So, we can represent each of this by a 4 by 4 matrix. Okay. This is a 4 by 4, 4 by 4 and 4 by 4 matrix, and if you multiply all this 4 by 4 matrices, we get a generalized homogeneous transformation matrix. Now, something important to note here is that at most to go from any frame to any other frame in space, you require these 4 transformations only. You can of course have more number of transformations, but the minimum number is 4, and this is what makes the DH parameters very, very important, and we always use the DH parameters for this. Now, let us go and look at what these parameters mean, or what. So, these 4 parameters have names. So, the first parameter alpha is the angle between the z axis, okay, measured about the x axis. So, the angle between the z axis is called alpha, and this is called the link twist. So, this angle is called the link twist, and it is the angle between the z axis. So, it is the angle between z I minus 1 and z I. The next parameter is a I, which is the distance between the x axis, distance between the z axis, and this is called the link length, right. So, link length is called a, alpha is called the link angle. The next parameter is called di. So, di is called the offset distance. So, the offset distance is the distance offset distance between the origins or distance between the x axis xi and xi minus 1. So, offset distance is the distance between the origins of the two frames, and it is the distance between the x axis of the two frames, and this is called the offset. When we say link offset, we mean the distance di, and the last one is called the link angle, which is called which is the parameter theta, and this is called the link angle. Or it is the angle between. So, this is the angle between the x axis of two frames. So, whenever I have written z axis, x axis, it means these two axes are for the two respective frames. Okay. So, it will be x zi minus 1 2 zi. Now, when a robot is made, or after the robot is made, the twist angle will normally remain constant, the link length for a revolute joint robot will remain constant, the offset distance will remain constant. The only variable here is angle theta. So, if you look at when the robot moves, a planar robot moves, what changes is essentially this link angle changes, all these three are constant. So, something to note here is when the robot moves, essentially, so for a revolute system, revolute joint robot, when the robot moves, only theta changes, and for a prismatic robot, prismatic joint or prismatic robot, then what changes is d changes. So, what is d? D is the distance between the is the offset distance, right. Now, these 4 parameters are basically what, using these 4 parameters we define what is called the DH parameter table. Okay. So, let us look at the DH parameter table next. So, using this 4 parameters we make the DH table. Okay. So, let us look at the example that we just did, which I showed in the robot which is there. So, this is 3 links which are there. Okay. We assigned our frames Z0, Z1, this is my Z2, this is my Z3, okay. And X0 is here, X0 is here, X1 is here, this is X2 and this is X3. So, we have fixed our Z axis and X axis, and Y axis is not required. Let us write down the link lengths, this is L1, this is L2 and that is L3. Okay. So, now in the DH we have to make our DH parameter table. Now, the DH parameter table contains these parameters A alpha, D and theta. Now, what are these 4 parameters? We have seen that if you want to go from any frame to any other frame, we are moving from this frame to this frame. Okay. So, we are moving from this frame, finding the relation between this frame and this frame. So, essentially there are 4 parameters and they are A, alpha, D and theta. So, the DH parameter table also consists of these 4 parameters, and this is my A, alpha, D and theta. How many joints are there? 1, 2 and 3 joints. So, this is my joint number 1, this joint number 2, this joint number 3. So, I have 1, 2 and 3 joints here, okay, for the corresponding joints, and we have our parameters A, alpha, D and theta there. Now, just when you are doing it for the first time, it is a good idea to write that A is the distance, okay, between the x axis, okay. Just to remember, this is distance dist between the x axis, this is the angle between the x axis, sorry, this is the angle between the z axis, sorry, this is distance between z axis, okay. So, distance between z axis is A, the angle between z axis is alpha, distance between x axis is D, and angle between x axis is theta. So, just to remember, you can very quickly write down on top that this is the distance between z, this is angle between z, this is distance between x and this is angle between x, and they correspond to the corresponding DH parameters. So, here how do we proceed? So, let us proceed here. So, the first joint is 0 and 1. So, it is 0 to 1, this is 1 to 2, this is 2 to 3. So, this basically means the relation of axis 1 to axis 0. Now, if you look at the axis 1 and axis 0 here, then what you can see is my Z0 and Z1 are here, X0 is here and X1 is here. So, when this manipulator rotates, what will change? If it rotates anticlockwise like this, what will change is that angle theta 1 will change, right. So, this is my angle theta 1, this is my angle theta 2, and that is my angle theta 3. Okay. Please note that this is theta 2 is with reference to theta 1 and theta 3 is with reference to theta 2. So, this is not with reference to the horizontal. So, in the first case, what is the parameter A? It is the distance between the z axis. Now, z0 and z1 are the same axis, so there is no distance between them, so it is 0. Next is the angle between the z axis. Again, the z0 and z1 are the same axis, so there is no angle between them, so it is 0. Okay. Now, what is the distance between the x axis? Now, if you note that x1 is here and x0 is here, so they are both intersecting at this origin at this point here. So, essentially there is no distance between them, and because of which the distance is again 0. Now, when the manipulator moves, suppose it moves like this, what will change is the angle between the x0 and the x1 will change, right. So, my variable angle is theta 1 here. Okay. Again, if you look at the second joint, the second axis is here. So, z2 is here, z1 is here. Okay. So, this is my z1, this is my z2. Okay. Now, this is my x1 which is along this link, and x2 is along this link, right. So, now if you look at for the second case, the relation between frame 2 which is here and frame 1 which is behind, which is frame 1 is fixed to frame 0, then what is the distance between the z axis? So, the distance between the z axis is this length L1. So, this is my link length L1. So, the distance from this z to this z is my link length L1. So, I get link length L1 here. Next is, what is the angle between the z? Now, this z1 and z2 are parallel, as you can see. Now, if two lines are parallel, there is no distance between them, if the two lines are parallel, then there is no angle between them. So, the angle is 0, right. And what is the distance between the x? Now, if you look at x1, x1 is along this direction, this is my x1 if I extend it, okay. x2 is along this direction. So, what is the angle here between x1 and x2? It is the angle between the x's are theta 2. Okay. Now, the x1 and x2 are intersecting at that point, and hence there is no distance between them, it is 0. Now, next the third one, if you are looking at we are trying to find the dh parameters indicating the relation between the third axis and the second axis. So, in that case the origin of the third axis is here, the x2 is pointing in that direction, okay. Z3 is in this direction, that you can see. So, if you look at the first parameter A, what is the distance between the z? Now, Z2 is here and Z3 is here, they are parallel. So, what is the distance between them? It is this L2, which is the link length, okay, which is indicated here. Next is, what is the angle between them? Now, Z2 and Z3 are parallel, so there is no angle between them. So, the angle is 0. The third parameter is the distance between the x axis, as I just indicated that x2 is in this direction and x3 is in that direction, and they are intersecting at this point here, right. So, what is the distance between them? It is 0 again. And what is the so when this link 3 moves, if you can imagine link 3 is moving, what will change is this angle here is going to change, okay. So, my variable is theta 3, okay. So, this gives us the dh parameter table, and this table is used for finding the relationship between one frame to the other frame and then multiplying it out. So, let us use this relationship, let us use this table and find out the transformation matrix. What is it that we want? We want the relationship between the third frame, that is frame number 3, and frame number 0. So, in that case, whenever frame number 3 is moving in space, I can find its relationship with respect to frame number 1. So, this will mean that I need 3 matrices. T0 to 3 will mean T0 to 1 cross T1 to 2 cross T2 to 3. So, I need to find the first one, relationship between 0 and 1 and 0. Second is relationship between 2 and 1, and then relationship between 3 and 2. So, let us write down the first matrix. The first matrix is T0 to 1. Now, if you go back here to our homogeneous transformation matrix, which we just derived some time back, then essentially this matrix looks something like the matrix essentially is here. So, it has a 4 by 4 matrix and the first part of it here is the rotation matrix. Okay. So, this gives us the rotation between the two frames, rotation about z axis. So, the structure of the matrix remains the same, it is a rotation about z. So, this will be 0 0 1 0 0 1, it will be cos minus sin sin cos. This is the distance between the origins of the two frames. This is always 0 0 0 and this is always 1. Now, once we remember that, what we can do is essentially we can write down these matrices simply by looking at the frames. Okay. So, let us see if we can do that here. So, I have T1 to 0, which basically means is the first one. So, this will always be 0 0 0, that will be 1. Now, if you look here, the frame 0 and the frame 1, they have the same origin. So, when it is rotating, it is a rotation about z. So, it is cos theta 1 minus sin theta 1 0 0 1, it is sin theta 1, it is cos theta 1, it is 0 0. Okay. So, we have got the rotation matrix. Next is the distance between the origins. Now, the origins of both of them are the same. So, this is 0 0 and 0, right. So, simply by observing we can also write the transformation matrices. Now, the second one is given by this matrix. Again we simply write 0 0 0 and start off. Now, your axis 2 is here, origin is here at this point, and axis 1 origin is here. So, origin 1 is here, origin 2 is here, right. So, what is the relationship between these two? So, when the link 2 is moving, what is changing? It is rotating by an angle theta 2 about the z axis. So, again this is going to become cos theta 2 minus sin theta 2 0 0 1 sin theta 2 cos theta 2 0 0 1. Now, what is the distance between the origins? The first origin is here, second origin is there. What is the distance between them? It is L1, L1 along the x axis, right. So, my x1 is in this direction. So, this L1 is the distance between the origins in the x direction. There is no distance in the y and no distance in the z direction. Now, the third one, if we can write 2 to 3, the third frame, we can write it in the same way. I say 0 0 0 and then see where is my frame 3. Frame 3 is at this point, frame 2 is here. So, when the frame 3 rotates, what happens is, what changes is angle theta 3 changes, right. So, it is again a rotation about z. So, you can imagine that there is a rotation here. So, that is my theta 3. So, a rotation about z would mean cos theta 3 minus sin theta 3, it is 0 0 1, it is sin theta 3 and cos theta 3, and this is 0 0 1. What is the distance between the origins? Second frame origin is here, third frame origin is there. What is the distance between them? Distance between them is L2. In which direction? In the direction of x2. Okay. So, L2 in the direction of x2 or the x axis, and that is 0 0 0. Right. So, next what we will have to do is we will have to multiply all these 3 matrices, and once you multiply all these 3 matrices, you get the total matrix, which will take you from the first frame to the so let us look at multiplication of these matrices. So, today we will end here. So, today's class essentially we discussed about the homogeneous transformation matrix, and the important parts of the homogeneous transformation matrix is you need to know the structure of the homogeneous transformation matrix, which is very very important. Now, in robotics, apart from doing all the mathematics, like this is a matrix and matrix multiplication, we have to correlate that to the actual system, the actual robot. So, when the robot is moving, we should exactly know that in this homogeneous matrix part, which part corresponds to the rotations, which part corresponds to the translations, and then we will be able to very easily write the homogeneous transformation matrix. And in the next class, what we will look at is when we multiply these matrices, we get the final matrix, which will give us the relation between the third frame and the 0 frame in the case of this manipulator system. So, we will stop here for today. Thank you.